Hello and welcome. Thank you for joining us today on this webinar on gas contamination and LineVu. We're going to be talking about gas systems, improving their efficiency, hopefully quite substantially. I'm going to be taking you through some of the problems we see in the field, showing you some videos, and then going behind the scenes and seeing how LineVu works in more detail. My history is with dew point measurement and gas analysis, and over the years we've come across problems that the industry perhaps is not tackling as well as it could. The problem we want to solve is liquid carryover and the industry's blind reliance on gas separator performance. This new technology can improve both safety and profits, and it's rare to get both of those in one hit. Liquid carryover is the cause of the vast majority of process upsets: plant damage, foaming, explosion, errors in flow measurement, the list goes on. In the oil and gas industry, the way we separate oil and gas is quite critical, and yet there is nothing that will permanently and effectively monitor the gas separator's efficiency. And that leaves the operators in the dark, running processes downstream of separators and just having to cope with liquid carryover that happens on occasions or sometimes continuously. A few years ago, we wanted to get our heads around how gas with low levels of liquid behave and perform this simple test. This 2-inch diameter perspex pipe has air running at around the velocity you might expect in a gas pipeline. We are injecting oil in the middle of the pipe. As you can see, the speed of the gas throws much of the liquid to the pipe wall, and as we move away from the injection point, the liquid slowly makes its way to the bottom of the pipe. This is where engineering meets art, and you can see what is known as a full annular flow. The liquid forms a film around the inner circumference of the pipe. Moving further down the pipe, more liquid travels to the bottom and starts to make a thicker layer. As the liquid is only moving through the pipe because of friction with the gas, the liquid layer at the bottom of the pipe begins to move quicker than that on the side. The process of the liquid travelling to the bottom of the pipe continues under gravity and would eventually end up with a stream of liquid just at the bottom of the pipe. So let's take a look at where liquids might come from in a gas network. Starting at the wellhead, water, sand, crude oil that includes natural gas liquids all come up with the gas as it leaves the gas well. In addition, liquids are added to the gas flow at the wellhead. Bactericide, corrosion inhibitor, and hydrate mitigation liquids are commonly present in the gas as it leaves the wellhead area. At this point, the only interest is to keep the gas flowing in a safe condition. Hydrates are the scourge of the industry, and we've got some work to do here, but we think we can detect hydrates at their initial stage. Several gas wellheads are typically connected to a single gas processing plant. In this illustration, we've shown twin gas processing trains. In many gas plants, there may be 3, 4, or even 5 gas trains, offering some level of redundancy for maintenance. The first action with gas treatment is to remove the liquids and solids in the incoming gas. This is the most important gas separation in the gas treatment process. The only thing moving forward into gas treatment should be gas. The first process, usually, is desulfurization. This process removes hydrogen sulfide and carbon dioxide. The most common method for removing these contaminants is to use an amine-based liquid. In this example of a gas treatment tower, gas enters the tower at the bottom and makes its way to the exit of the tower at the top. The processing liquid, in this case amine, enters the tower at the top and makes its way to the bottom of the tower via a number of bubble trays. There is a reaction that locks up the CO2 and the hydrogen sulfide in an unstable salt in the amine. The amine leaves the tower at the bottom, is then depressurized in a flash drum and sent to be regenerated. It is a high temperature process that releases the gases that have just been captured, and the amine then returns in a loop back to the top of the tower. There are several triggers for foaming in gas treatment. Liquid carryover causes two of the major triggers. In the short term, surfactants in the gas stream cause foaming. If it happens, the gas flow must be reduced by 50% or more and defoamer added. The operator monitors the differential pressure between the inlet and the outlet, and once they believe that foaming is under control, gas flow can start to be increased again. Depending on the severity of the foaming event and the plant size, a foaming event can cost between $250,000 to $250 million. In the long term, hydrocarbons entrained in the gas stream will turn to carbon during the processing liquid's regeneration process. This causes a buildup of solids within the processing tower, and if not filtered out, can be a second cause for foaming. Foaming is a big issue with gas treatment. When foam happens, it can overrun the demister pad at the top of the tower that separates the amine from the gas as it leaves the tower. The amine carries over and contaminates the liquids used in the next gas processing stage, gas dehydration. In this process, a similar tower to the previous process is used, but this time a glycol-based liquid is used as a liquid desiccant to dry the gas to a low level. The gas is dried to a level that conforms to the gas pipeline entry requirements. Again, a demister pad should prevent glycol from carrying over with the gas flow. At this point, the gas is sweet and dry, so the next step is normally to remove as much natural gas liquids as possible during a process known as dew pointing, or NGL removal. Butane, propane, and other natural gas liquids are premium products, and often the gas supplier is paid more for these liquids than the natural gas, which is primarily methane. This process normally reduces the gas temperature to a low level, usually -20 or -30 degrees C. If glycol is entrained in the gas, it will freeze. When the gas reaches the custody transfer point to the gas transmission network, it should comply with the network's quality requirements. This usually means the maximum level of hydrogen sulfide and water vapor is specified, and that there should be no liquids or solids contained in the gas supplied to the network. So before we get into too much detail about how LineVu works, let's take a look at some of the footage we've captured of contamination events. LineVu is a camera system mounted on top of the pipeline, and it looks down to the pipe below. So this, first of all, is a normal gas flow. Imagine you're sitting on top of the pipeline, looking straight down from above. This is the view of the pipeline floor, and gas is moving rapidly from left to right. You can see a couple of features on the pipe floor. There is what appears to be a scratch in the middle, some fixed material on the right. These are good reference points when things get busy. The image is moving around a little, and this is quite normal for pressurized gases. We use these time-lapse videos to review a 24-hour time frame in 57 seconds. It shows up any contamination event that is below the alarm threshold. A weekly report includes these daily videos and is sent to the client for review. This footage from a 36-inch diameter pipe is on a gas network. The gas should be compliant with sales gas standards, but the network has installed an extra separator downstream to catch anything that might come across from the supplier. So this is the user interface, and on the left you can see a time and date stamp at the top. The details of the client and location have been removed, and then there is housekeeping data for the unit underneath. At the bottom on the left there are settings for focus and illumination, all of which can be changed remotely. On the right there is a measurement scale to give users an idea of the size of the events that they're looking at. This is the following day. Again, a time-lapse video that shows liquid contamination that appears suddenly, moves up the field of view, collapses and falls back down. Later in the day, more contamination can be seen together with a light mist flow. Mist flows reduce the total amount of light received by the camera. In this case, it's purely a light mist flow, as we can still see features on the pipe floor. This is a section of that day in real time. the liquid flow would appear to have high surface tension and so are unlikely to be NGLs. You can see that in reality, the liquid flow is extremely slow, and this has been measured at 2 meters per hour. You may have noticed the liquid flow is at a slight angle to the gas flow, and this would indicate that the gas has a slight helical flow at this gas velocity. On this day, multiple small but continuous streams move across the field of view in alignment with the gas flow. Previously, the contamination had a high surface tension, giving it a compact flow stream. In this case, the surface tension is much lower, leading to multiple smaller flow streams. These have been analysed and run at about the same speed as the previous flow, around 2 meters an hour. In this last example, we can see more of a film with crescent-shaped waves on the surface. At each side of the wide film-like flow are more compact snake-like flows. Interestingly, the snake-like flows at the edges are moving quicker than the film flow at the bottom of the pipe. If liquids and solids enter a gas network, they will slowly travel through the network and accumulate at a low point. If these liquids contain water or corrosive materials, they can cause internal corrosion to the pipeline. Without monitoring systems for liquids, gas networks continue to be at risk. Once in the network, gas pools at a low point in the network, causing internal corrosion that can lead to rupture, as at Carlsbad, New Mexico. The rupture and explosion created a 51-foot diameter crater with approximately 49 feet of underground section of pipeline ejected in 3 pieces from the crater. A large fire ensued, killing 12 people. The National Transportation Safety Board investigation concluded that internal corrosion was the likely cause of the event. The blocking of a drip upstream of the rupture site allowed liquids into the pipeline section. The drip was a 40-foot long stub line branched off the bottom of the gas pipeline and designed to collect liquids and solid from the pipeline. The drip was found to contain a blackish, oily, powdery, grainy material at the area of its heaviest contamination. The investigation concluded the event was a likely result of the drip's partial clogging upstream of the rupture location. Some liquids bypassed the drip, continued through the pipeline and accumulated, causing corrosion at the eventual rupture site, where pipe bending had created a low point in the pipeline. Had the network effectively monitored the quality of the gas entering the pipeline, it would likely have determined the potential risk existed for significant corrosion to occur. So, if there was an effective method to monitor these liquids before they enter the network or before they enter the process, separator faults could be diagnosed, saving suppliers millions of dollars on processing liquids and the loss of NGLs. And networks can optimize pigging processes only to those lines that have seen contamination. So this is what a pig should look like on the way in, and this is what it looks like on the way out once it's done its job. When conveying gas in high pressure transmission lines, it's important to move the gas quickly, and to achieve this, a compressor station is installed every 100 miles or so. When contaminants get into the network, they cause further problems for compressors. When liquids get into gas seals, internal leakage can cause damage to the compressor. In extreme cases, when slugged flow occurs, the liquids do not compress and an explosion is usually the outcome. The point of use for natural gas could be to convert it to LNG in a liquefaction plant. To achieve this, the gas has to be dried to just 1 part per million or lower in a molecular sieve dryer. Contamination of these dryers causes molecular sieve to be written off. Clean fuel gas is an important factor for the petrochem industry and for gas turbine power stations. When liquids are entrained in the fuel gas, they are deposited on the turbine blades and either build up a deposit, or if they are hydrocarbon liquids, they can create a hot spot and burn a hole in the turbine blade. Either way, the turbine then goes out of balance and causes severe damage. Our mission, quite simply, is to stop pipeline contamination. And we have a piece of kit that we hope will help with that. So this has become an exciting area, one that's not well understood, and there are differences between test flow loops and real-world conditions. So here we have the camera can sitting on the pipeline. So it's certified for use in hazardous areas, Class 1, Div 1, or ATEX Zone 1 or IECX Zone 1. And the flange here is a Class 900 3-inch RTJ. And the ring type joint, or the RTJ, centralizes the camera on that vertical section. So between the camera can and the pipeline is normally a flange adapter, because the site standard flanges are not normally the Class 900 3-inch flange. Sometimes we can put a vent on the flange adapter, and that allows us to safely vent the section here when we're taking the LineVu off. This section between the flange adapter and the tapping point is there just to represent the valve that would normally be there, the isolation valve, which could be a single isolation or maybe a double block and bleed. Now the tapping point we've got here is a 2-inch tapping point on an 8-inch line, but obviously in reality we're going into much bigger pipelines, 12-inch, 24-inch or even bigger than that. So the camera can is stainless steel and electropolished as well. In a hot environment we put it perhaps a sunshade over the top, and if it's particularly cold, minus 40 for instance, then we'd put a heat jacket around it to keep it up to a normal sort of temperature. This space here between the pipeline and the camera can is actually a dead leg. There's no gas moving here, and that gives us the cushion that we need to keep those optics clean. So let's take a look at the camera can in more detail. And what we have here is 2 chambers, in fact. The upper chamber is a certified enclosure for use in hazardous areas. And then around the bottom is a secondary containment vessel. So the secondary containment vessel is there so that if we do have a leak on the window or maybe a seal on the window puck, then we have a safe area and there's no loss of containment. And that's what gives us the level of safety that is sufficient to attach this equipment to gas pipeline networks. So this is the window puck, and we have the camera and the heatsink here for the illumination. So the illumination produces a little bit of heat, which we distribute to the window, and this is the sapphire window at the bottom. And that's gently heated so that if there is condensing conditions in the pipeline, we don't see condensation on the window. And then the window puck assembly slides up inside the secondary containment and is bolted in place. So safety is a big thing about everything that we do. And the camera can goes through 3 different pressure tests. We first of all press the upper chamber and then test the lower chamber, which includes the process connection. And then the whole assembly goes on a 3rd test in these temperature controlled pressure stations. And that tests all the internal seals. We leave this on for around a week, more if we can, to make sure that there's no internal leaks within the system. So moving from the camera can to the interface unit. So the connection between the two is an Ethernet connection. So if it's copper cable, we can go up to 100 meters. If it needs to be further than that, then we would convert to fiber optics. The interface unit sits in a safe area, which is normally a kiosk or a local instrumentation hut, or maybe the control room if it's that close. And this normally does the power distribution and sends 24 volts to the camera can. If it's a long distance, then we might pick up that 24 volts locally. But on top of that, then we've got the connection to the mobile phone network, and there's space here for alarm relays that aren't in here yet, and maybe a Modbus connection to the SCADA system or the DCS system. So having a mobile phone network means that we've had to think about cybersecurity from day one, really. And the connection between here and our own server at our premises is a secure link. We also encrypt the data to make sure that that's safe as well. Then the LineVu controller is where we save the data, and we always save the data on site. So this link between the interface unit and the LineVu controller can be local. They're normally side by side, but they can be remote as well. So this could sit in a server room somewhere with a fiber optic or a copper connection between the two, again with an Ethernet connection. If the installation is on a manned site, then it's from here that there is a link really to the control room, and we can provide the control room with high definition live video of pipeline activity. So it's from here, it's from the LineVu controller that the web interface is also supplied. So the benefit of LineVu are for both gas supplier and gas networks. Gas treatment plants can use LineVu to optimize the gas flow through the plant, and this will change from day to day with temperature changes and with fouling buildup in separators affecting their efficiency. If there are faults with gas-liquid separation, they can be highlighted and dealt with immediately, rather than waiting for the problem later down the processing train and recovering using defoamer or scavenging liquids to treat the symptoms of liquid carryover. Gas networks can use LineVu to ensure the gas entering their networks is free of liquids and complies with tariffs and other legal requirements to transport gas in a pipeline. If you'd like more details, then please email info@processvision.com. Thanks for listening, and hope to see you again soon.